Welcome everyone to the first colloquium meeting, live colloquium meeting this year. We're very pleased to have Tal Linzen with us. Tal is a faculty member at NYU. Prior to that, he was at Hopkins, also faculty member, and he did his postdoc in Paris. Better? So Tal is a faculty member at NYU, and before that he was at Hopkins, and he was a postdoc at École Normale Supérieure in Paris, and a PhD student also at NYU. And today he's going to tell us how well do neural NLP systems generalize. Just before starting, I would like to remind all of you that haven't been participating in live sessions in the recent months to make your phones silent, please. Good luck, Tal.
Thank you. So is the mic on? Yeah? Okay, great. Well, thanks for having me here. No? Okay, right, yeah. All right. I want to reassure everyone that I am vaccinated, and I will. Yes, it's okay, I suppose. Okay, so let's start with what I mean by neural NLP systems. So I think a lot of you have used language technology in the last few years. Basically, every system that you will use will have some neural network component in it. And these artificial neural networks, which are kind of elaborate function approximators, have been shown to be kind of astonishingly successful at various language technologies that I think if you asked most people 20 years ago if they thought neural networks would be able to do these tasks, they would say you're hallucinating. So this is just an example from machine translation. You take a large corpus of parallel text in two languages, just examples of a sentence in English and its counterpart in French, and you encode them as vectors of numbers. Each of the words is encoded as a vector of numbers, and then you just give it to this massive function approximator, and it learns a function that can then take a novel sentence in English that it's never seen before and translate it into a perfectly reasonable sentence in French. This is really quite astonishing. If you're a linguist, say, and you think that to be able to do anything sophisticated with language, you need very elaborate symbolic representations that these neural networks really don't have. So just one brief slide on what neural networks are for language processing. As I said before, you take each word and then you encode it as a vector of numbers. These numbers themselves are also learned as part of the training of the network. And then you take that vector, you pass it through a number of very simple arithmetic operations that are all learned as well. So it's basically a long sequence of weighted sums followed by nonlinearities. And then at the top layer of the neural network, you can decode an output. The output can be a French word or an English word or some label that you care about. So again, what happens in each of those layers is this extremely simple operation. And there are some embellishments, but basically it's all extremely simple math that doesn't include any symbolic representations of language of the sort that we used to work with in NLP and linguistics and AI. Now, these systems, according to most of our benchmarks, are performing extremely well. Some benchmarks actually appear to show that they understand language even better than humans. So this is a massive set of numbers. You don't have to care about what those numbers are. It's what's called a leaderboard, and a leaderboard compares all of the latest models that have come out of the NLP community on a set of standard benchmarks. So one of those standard benchmarks is called MNLI. I'll say a few more words about that in a bit. So you can see that the best model as of January 2020, so more than a year ago, scores its accuracy is 92.2% in this data set. And all the way down at the bottom of the slide, the human accuracy on this data set is 92%. So we have neural networks that understand language as well as humans do, if you believe that accuracy on this data set reflects language understanding. So let's start by taking a closer look at this particular benchmark. I'm not going to go through all 10 of them. So what is MNLI? So this it's a data set that has examples of the natural language inference task. The idea in natural language inference is you get two sentences and you need to determine if the second sentence in red follows from the first sentence here in blue. Meaning every time the blue sentence is true, then the red sentence also has to be true. So if that's the case, which in this particular example is in fact the case, where if there's a soccer game with multiple males playing, it's also true that some men are playing a sport, then you're supposed to give it the label entailment. In other cases, if the two sentences couldn't possibly be true of the same situation and entity, you're supposed to give it the label contradiction. In this case, if the man is inspecting the uniform of a figure, then it's very implausible that the man is also sleeping. So to do this well for any pair of sentences, you really need to have a very deep understanding of language. So it's quite impressive that a neural network that is just trained on a bunch of examples of this task is able to do so well. Yeah?
Does the network need to know that soccer is a type of sport?
To any, either if you're human or a computer, to perform this task well, you need to know that soccer is a type of sport. But it's not taught that explicitly in the paradigm that we're using now. It just picks it up from a lot of examples, essentially. So yeah, it's one of the many things you need to know about language and about the world to be able to do this task well. In fact, you can argue that you can rephrase any AI task that has to do with language in this format. So 100% accuracy means that, in a sense, you've accomplished AI. Okay, so but then obviously if this was really the case that we have computers that are as good as humans at this task, I wouldn't be standing here and talking. We could have closed the computer science departments and moved on to more important things. But the fact is that there are actually this is a misleading. I mean, the statistic that we're seeing, the 92% accuracy, doesn't reflect exactly what we want it to reflect. So what do these evaluation metrics that we see in the leaderboards in fact reflect? So the way that most of these evaluation data sets are constructed, you go to Amazon Mechanical Turk, which is a platform where you can recruit people to do simple tasks for you online. And you give them a bunch of sentences and you ask them to generate sentences that follow from those prompts or that contradict those prompts or maybe are neutral with respect to those prompts. So you get a large number of examples, let's say 300,000 of them. You give this task to a lot of people on the internet and you pay them 7 cents per sentence. And then what you do is you split this a large number of examples into a training set and a test set. Right? So the model is trained on the training set, and then it is tested on the test set. It doesn't see the examples from the test set in training. This is kind of the standard machine learning paradigm. So in the last few years, the field of NLP have converged on a very specific way of performing these language understanding tasks. So before you use this training set and test set that give you example of the task that you want to solve, you start by something called pre-training. So in pre-training, you don't try to solve any specific language understanding task. You just try to predict the next word in the sentence, or you give the model a sentence with one of the words masked out, like there's a gap in the middle, and you have it predict what that word that's missing was. So in this case, if the original sentence was birds can fly, the input to the model will be birds can mask, and the correct output would be birds can fly. Right? So the word fly there gives the model supervision that it can then use to adjust its parameters, so next time it's more likely to predict the word fly. So this gives us a pre-trained language model. This particular example is BERT. It's a very widely used language model that we're also going to see. We're going to use it ourselves in a bit. And another term that I might use later is TRM here, that stands for transformer. That's just one arrangement of one neural network architecture. It doesn't really matter to understand what the details of it for the purposes of this talk. We're just going to treat it as a black box, but there aren't any sneaky linguistic representations in it. It's still a lot of matrix multiplications, basically. So this stage, we do this for a very large number of sentences. BERT was trained on 4 billion words. So you mask one of the words, and you have the model predict that word in a 4 billion word corpus. And then you take the trained model, and you use that to perform transfer learning to the task that you want to evaluate it on. So in our case, the task was NLI, the natural language inference task. So we get from BERT vector, that little C vector at the top left corner, that gives us a representation of the two sentences. And then we additionally train a classifier on top of that vector to perform the task that we want to perform, the inference task. And then we evaluate on the test set, and we can update the leaderboard if we got a better score than the previous model. So this form of evaluation, what I really want to draw your attention to is that the training set and the test set are produced through the same data generating process. But what we really want our model to do, and the way that we want to evaluate that the model is able to understand English, is by, we wanted to learn to perform the task as we humans think of it, right? That is not a controversial statement. And we think of inference as, does the second sentence follow from the first one? That's what we want the model to be able to do. But a neural network, it doesn't know anything about language before it starts its training, right? So we don't have any guarantee that the network will learn what we want it to learn rather than any other property of the data set. And especially when we train our network on data that was generated with a very specific process, for example, giving a bunch of prompts to people on the internet and asking them to generate sentences that follow from those prompts, then it's very plausible that a neural network that just doesn't have a strong inductive bias to care about language as opposed to anything else will latch on to the various quirks of the data generating process. So let's say if the people who generate the data like to use longer sentences for contradictions than for entailment cases, then the model will happily use that fact because there's no reason for it not to use it. There's no inductive bias telling it that the length of the sentence is not something that matters for logical inference. So what I want to do today is to shift the focus of evaluation from this in distribution evaluation, where the training and test set are drawn from the same distribution, to focusing on generalization. So, and the way that I will characterize generalizing as a human would is using linguistics. So the idea there is that we have, from linguistics, we have a very good formal characterization of what it means to understand language. And we're going to use that to create challenging evaluation data sets that may not be similar to the training set, but that is a virtue rather than an issue with this methodology. So what I want to argue is that what is really important is generalization to examples that are not similar to the training set. That is what really shows that you understand language. Because as a human, you have no trouble generalizing to sentences that are very different from anything that you've heard in the past. The purple giraffe flew over the mountain. This is not a sentence that's similar to anything that you've heard before, but you're able to understand it and you're able to draw inferences from it. I have three kind of case studies that I wanted to look at. We might not get through all of them depending on how many questions people have. So the first case study looks at the task that I just described, the natural language inference tasks, and evaluates syntactic generalization in this task. And then I have a couple of examples that a couple of case studies that test for zero-shot generalization. The idea there is that, unlike in the first case where there are a few examples in the training set that are maybe similar to the challenging evaluation example, in the zero-shot cases there are definitely no examples in the training set, and we know that because we created the training set ourselves with synthetic data. So this is a more challenging generalization setting. And in linguistics, you can call it the poverty of the stimulus paradigm. I'll say what that means in a bit. So then there are two studies, one on learning to form questions in English, where you have a declarative sentence and you're asked to generate the question that corresponds to that sentence. And the other one is semantic parsing, which basically means taking an English sentence and creating a formal logical form that unambiguously specifies the meaning of that sentence. And then I'll have some kind of bigger picture rant about what we need to do. Okay, so let me start with the first case study. So how, there's a question. Yeah.
The ground truth, these data sets, where did we get the ground truth from? Is it also crowdsourcing?
Yes, actually that is my next slide. So that's an excellent question. There are different ways to collect data sets, by the way. And some ways might be better than others. Maybe this particular data set with the crowdsourcing methodology can be tweaked and improved. But it remains the case that if you generate a data set using any process and then you split it at random to a training and test set, you'll potentially have the problem that I described before, where the model can recapitulate the data generating process as opposed to learn the task that you would like it to learn. So here's what they had the crowd workers do. As I said before, you get a prompt and then you need to write three sentences, one that is entailed by that sentence, one that contradicts it, and one that is neutral with respect to it. That's might be correct. So, right, if there are two people sitting on a chair, the first sentence and the second sentence is the bird is green, then those two sentences are not in contradiction, but also don't entail each other. So there are three possibilities here. And then they had the labels, as the question just asked, that was just asked. They had a separate set of crowd workers annotate the generated hypotheses for their label. And for the most part, there was a lot of agreement. So here, when the prompt was 8 million in relief in the form of emergency housing, the first crowd worker generated the sentence for the neutral label, generated the sentence, the $8 million for emergency housing was still not enough to solve the problem. And it's true that it's neutral. These two sentences don't entail or contradict each other. And the set of four additional annotators all agreed that this was the correct label. So you see there is one case of disagreement at the top, but for the most part there was high agreement on these things. Now, when we take the BERT model that I just described before, the one that first is trained to predict the identity of the word that is masked from the input, and then is fine-tuned on the language understanding task, we get very high accuracy. We get 84% accuracy. whereas a chance accuracy here would be 33% because there are 3 labels and they're equally likely. So this seems to be pretty good, but what we set out to do was to see to what extent the model is using the syntactic structure of the sentence to perform its logical inference task. So the approach here is that we come up with a hypothesis for something that we think is important for the task, and we are concerned or we have a suspicion that the model might not be using this aspect of the task in the way that a human might. So this is sort of a hypothesis-driven approach. And the specific concerns that we had were that the model would use lexical overlap heuristics to perform this task. So what do I mean by that? Trivially, every sentence entails itself, right? So it's not crazy to think that if you might get above chance accuracy just by saying that whenever there's high lexical overlap between the premise and the hypothesis, the label should be entailment if you don't have any other reason to prefer one of the other labels. But it turns out that there's a dataset specific issue here, which is when you give a crowd worker a sentence and ask it to generate a sentence that is entailed by it, they will often just take that sentence and maybe delete a word from it. Or maybe they'll add something that doesn't really change the meaning of the sentence. But they won't generate a sentence that is completely different from the prompt. This is just an artifact of the way that you collected the data. So we suspected that this is going to be an issue, that a neural network that doesn't have any inductive bias, as I said, to prefer using syntactic structure to perform the task, can use these simple heuristics. So let me give you an example of when the heuristic works. In this case, this is one of the sentences we constructed for the data set, for the evaluation data set we created. So if the sentence is the judge was paid by the lawyer, that actually entails the lawyer paid the judge. So here is the case where the lexical overlap heuristic works. But of course, it doesn't always work. You can make a very small change to this example, and it won't work anymore. The doctor was paid by the actor. It's not true that the doctor paid the actor. We tested a couple other heuristics that are kind of special cases of this heuristic, but I'm not going to go into the detail here. The subsequence heuristic is essentially the same, except the words are in sequence rather than potentially scrambled. That is not critical. So we took 4 models. We did this work a couple years ago. So these are not the state-of-the-art models as of today. But the best model that we had was BERT, and then we had 3 other models that I don't need to describe in detail. So as I said before, this is the accuracy on the data set itself, the original test set that came from the same distribution as the training set. Now let's see how the model does on the data set that we created. So the data set that we created is, you can think of it as adversarial in a sense, because it's a data set that if the model is using the lexical overlap heuristic, it will necessarily make a mistake on this example. It's examples like the second one here are the kind of examples that we created that we suspect the model will get wrong if it's using the lexical overlap heuristic. And the first class of example are examples that we know it will get right if it uses the lexical overlap heuristic. So we expect to get very high accuracy on examples from the first category, where the heuristic makes the correct prediction, and very low accuracy on examples where the heuristic makes the wrong prediction, like the second one here. And that is actually what we found. What we found was much more striking than we had expected, actually. We thought the heuristic would make a small difference, but it turned out to make an enormous difference. So let's start with the cases where the heuristic makes the correct prediction. You see that the accuracy here is really high. It's close to 100%. So accuracy on cases where the heuristic makes the correct prediction is actually much higher than the average accuracy, which already shows that maybe these cases are so easy for the model because it's using the wrong approach to solving them. But then when we look at the cases where the heuristic makes the incorrect prediction, accuracy is very, very low. So it's much lower than chance. Here, chance was 50% because we collapsed to the labels. So even the best model that we had at the time, BERT, gets accuracy of below 20%. So it does the opposite of what it is expected to do based on the structure of the task because it's using the heuristic, which is causing it to make an incorrect prediction. It's leading it astray. Yeah?
Just a question regarding what accuracy. Above we have examples which are only entailed, and below we have examples which are not entailed.
Right. Yeah, so the heuristic makes the correct prediction for examples where the label is entailed. Those would be examples like, like the first one here. The label is entailed. It's like the arrow doesn't have a line over it. So the model did extremely well on this class of examples, but did extremely poorly on the second class of examples where the label is not entailed. I'm just going to give you an example of how absurd this is. So there are a lot of different linguistic constructions that we use to construct this data set. I'm not going to go over all of them. I just wanted to give you one example. So it's a very simple case called the subject-object swap. So what we did is we flipped the subject and the object of the original sentence and created a hypothesis that way. So what all of these four models are getting close to 0% accuracy on this case, where so essentially they think that the lawyer advised the judge entails the judge advised the lawyer. Right? They're not really using the order of the words to perform the task. They're not really learning anything that syntax matters for this task. Yeah?
Just clarification. Did you train the network with counterexamples such as the second one?
No.
Okay, but that's the point, right? So if you didn't show the counterexamples, you expect the network to do that.
Right.
So the counter-argument could be that we need to give the counterexamples to the network in order to be fair.
Right. Well, so that is, yeah, that's a very good point. We actually did that experiment, and I have a few slides about it, which we can go over. But the bottom line is that it works, right? If you give the network counterexamples, it eventually figures out that it's supposed to use syntax to perform the task. So the network has that ability. It just doesn't like to do that. It doesn't have a strong bias to do it. So if there is a relatively small number of counterexamples, there are some counterexamples in the data set. So actually, maybe I can show that just this one of these slides.
No, that's okay. I just wanted to understand the issue of the training set. That's all.
Right. Yeah. So the training set has counterexamples. I guess what the model learns is obviously always a combination of its biases and the training data, and it appears that you need a very large number of counterexamples to steer it away from this simple heuristic, essentially. So just one more illustration of the fact that the model has a weak bias here. We repeated this experiment with different random weights, different random initial weights. So that's always when you train a neural network, you have to start with some random set of weights, and then with gradient descent, you gradually converge to a set of weights that gets you high accuracy on your task. But you can start with any set of weights you want. And the results were actually pretty striking. So when you look at the performance of those 100 models on MNLI or on the original data set, it's very consistent. So all of the accuracy is always between, 80% and, I actually don't remember exactly, between 83% and 84%. But then when you look at its accuracy on the challenge data set that we created, it actually varies quite significantly. I guess the most striking case is the bottom left corner. So we have, among our 100 models, we have some models that get close to 0% accuracy and other models that get close to 60% accuracy. So again, this is another example. Those are all trained on exactly the same training set. Just starting from different random points at random point in the weight space. So again, this is maybe not, this is consistent with what we saw before. The model doesn't have a strong bias to either use the heuristic or not use the heuristic. It seems like it prefers to use the heuristic because most of these models are have an accuracy of less than 50%, but still it varies very, very widely. So what this means is we get, what we've seen is that we get good performance on data that is similar to the training set, but poor generalization. The second set of results that shows how much variability we have illustrates is that the loss surface has a lot of local minima that probably have more or less the same score, but result in qualitatively different generalization patterns. So as we said, the inductive bias here is very weak. It does seem to favor the lexical overlap heuristic, but as I just said, if you add enough counterexamples, eventually it will learn the right thing. So it's not like there is some representational issue that the model is just incapable of doing the right thing. It just doesn't like to do it. It needs a lot of instruction to get to that point. So now, that might seem like a moot point. Why not just give all of those counterexamples to the model in the training set? And from a practical perspective, I agree with that. I mean, we actually published a paper that says, well, if you want to address this issue, you can perform data augmentation and just increase the representation of different kinds of counterexamples. And that's fine if what you want to do is improve the practical generalization performance of the model. But I think there's a deeper issue here, which is that I believe that we want to have our computers learn language from the distribution of sentences that exist in the world, and the fact is that there are often very few counterexamples to standard generalization, and sometimes there might not even be any counterexamples. And the reason that we generalize in a certain way is because we, as humans, have a very strong bias. So just like think of the situation where someone asks you to do something with language, gives you a couple of sentences, and you do have to do some creative task with those two sentences. Is there any way that you would approach that task without first reading the sentences and understanding them? Like, would you first try a lot of strategies that are based on whether the third word of the sentence began with a D, or whether the sentence has 17 words? It seems extremely unlikely that a human would entertain that hypothesis, at least at first, right? Your very strong bias would be, this is a sentence in English, I'm going to first understand it, that's going to help me do the task. And it doesn't seem to be that our models have that particular bias. They're very easily lured by those simpler heuristics. So I guess now is a good time to pause for a question. Yeah. Yeah. Bird base, for this example. Right.
You don't learn anything, and you can perform classification tasks with a model which is not trained for classification.
I haven't used GPT-3, so I have applied for access 6 or 7 months ago and haven't heard back from OpenAI yet, which is ironic given the name of the company, but they're not eager to let academics use that. A apparently I've heard that if you have a startup that might purchase their services, you're more likely to get access to GPT-3. So I have a friend who works for an astrology app who got access to it, but I haven't been able to do that. Anyway, but yeah, I think that I'm curious to see what will happen there. But what I do know from the GPT-3 paper, from the published results, is that actually inference is one of the tasks that it did very poorly on. But I don't know why, because I haven't done any follow-up experiments, obviously. Yeah. Yeah. Mm-hmm. Yeah, let me. I should have just. Yeah. So this is the. I guess we can focus on the leftmost panel here. What this shows is of the examples that the heuristic applies to, meaning of the examples where all of the words in the second sentence appear in the first sentence, what was the label in the training set? So I guess we had more than 2,000 cases where the lexical overlap meant that the label was entailment, and only 200 or 300 examples where the label was contradiction, even though there was lexical overlap. So, as I said before, there is this imbalance in the training set, but which you can fix. But it's not like there are zero examples for contradiction in the training set. So yeah, I guess as you can see, here in blue, I kind of leading to the experiment where we give it explicit evidence against the heuristic. I just didn't want to get into it today, and I hope to talk about some more recent stuff as well. But yeah, that's a good question.
What's the total size of the data?
300,000 cases. I'm gonna take this off. Was another? Yeah. Go ahead.
You talked a lot about inductive bias.
Uh-huh. Right.
Those other models have used such inductive bias over syntax?
Yeah. So that's a good question. I was going to. I'm going to show. I think that I'll only do the second case study because the third one probably not going to have time for it. But I'm going to show an example of that in the second case study. You would think that basing the neural network on the parse tree of the sentence would solve this problem. You can construct neural network architectures that are based on symbolic parses, and that's what we're going to do in the second case study. But in this case, it actually wasn't sufficient. So sometimes what happens is that you think that your architecture gives the model a certain inductive bias, but empirically it doesn't. So it's, I think, an open question. What is the best way to address this issue? But, yeah. Yeah, in the back.
Check if the problem is caused by the language understanding or maybe the task understanding. Maybe Bird understands English fine, but he doesn't know what I'm telling him. He knows this is a great way to get good results. He has no idea what I'm asking him to do.
Yeah. That's a really good question. So how would you distinguish those possibilities?
Bird was trained just on raw English text.
Right.
Never
No, but how?
trained to do intelligence.
Right, but then you kind of do the transfer learning.
Intelligent test is just a classic machine learning test. It makes a lot of sense that we'll learn some biases which have nothing to do with language.
Right. So, what do you propose as a way to test whether it understands language independently of the task? You're just saying that this. I mean, maybe you're right. Maybe what you're saying is that this paradigm just doesn't test language understanding.
Maybe this is like
Yeah.
you'll take a little kid, he understands English, but he was never encountered with a telling test, will do very
Yeah. No, I mean, I think that's a very valid criticism. I guess within NLP it would be a pretty radical criticism of the whole approach that we have for evaluating understanding. Because the way that we typically evaluate understanding in the field is by taking the language model like BERT and fine-tuning it on understanding tasks. So you're saying that that approach is not the way to go, that we need to evaluate understanding in a different way. And I actually might not disagree with that, but I guess we need to think of an alternative then. It's a good point. All right, well, let me show you the second example. The second example is nice because it's a synthetic data set, so it's maybe easier to understand what's going on, and we can also kind of solve the problem by giving the model very strong inductive bias that causes it to generalize in the way that we want. So let me show you what we did there. Go back to... So what the task that we're working on here is a kind of a classic example in linguistics for human inductive biases. And that's yes-no question formation in English. So I'm sure if anyone here has taken kind of the generative syntax class in a linguistics department, they've seen this before. So to form a question in English, what you need to do is take the auxiliary that precedes the main verb of the sentence and move it to the beginning of the sentence. So if the input is the zebra does chuckle surfer, these very silly examples, that's what happens when you create a synthetic data set and your student is 22. But no, it's fine. It's, you know, we needed the nouns and we needed verbs, and this is what we ended up with. But if you think about it, this is what Chomsky pointed out. This sort of example is actually consistent not just with the correct generalization, which is, take the main verb, find its auxiliary, and move it to the front of the sentence, but also with a simpler generalization, which is move first, right? You just scan the sentence from left to right and move the first auxiliary you find to the beginning of the sentence. And the sort of examples that children see, according to Chomsky, are completely ambiguous between these two rules. This example definitely is. But it's not like those two rules are always equivalent. There are some cases that disambiguate those two rules. And those cases are the ones where there's a relative clause modifying the subject. So if the input is, my walrus that will eat can giggle, here the first auxiliary is will, and the main auxiliary is can. So there are two different words, and you can infer from the behavior of your system on this class of examples which of the generalizations it acquired from the training set. If it acquired moving the main auxiliary, it will be, can my walrus that will eat giggle? That is the correct way to ask a question here. If it acquired the other generalization, move first, then you get the question, will my walrus that eat can giggle? This is a very weird question, and no one would ever produce it. So what Chomsky argued is that this, the fact that these examples are absent from the child's input, and yet children generalize according to move main and not according to move first, indicates that children have an innate inductive bias that tells them that the rules of language have to make reference to the structure of the sentence. We just don't have rules in human language that are based on the linear sequence of words. Every time you get a sentence, you need to first figure out what its structure is and apply the rule to that parse of the sentence. So when you have this sort of very strong inductive bias, then you won't get results like the results that we saw in the first part of the talk, where the model just ignored the structure of the sentence and instead used some other heuristic that happened to be effective in the training set. the next thing we're going to do is an experiment to see how neural network architectures generalize which of the two rules they acquire. And then we'll see that they actually, for the most part, acquire the wrong rule, the simpler rule, from their perspective, which is move first. And then we'll see how we can adjust them so they do acquire the correct rule. So what we did is, again, we showed a neural network that had the same architecture as those machine translation models, where you get a sentence as the input and you need to produce a sentence as the output. But you see there's this weird alternating color scheme here that indicates that the auxiliary here is both the first auxiliary and the main auxiliary. Those are sentences where the two auxiliaries are coincide. They're the same one. So we gave it some cases where it's supposed to form questions and some other cases where it's supposed to just return the input sentence and spit it out as an output. And the reason we had those identity cases is we also wanted to give the model some exposure to sentences that have a relative clause on the subject. But the crucial thing is that we don't want the model to know how to form questions about this type of sentence, because this is the type of sentence that disambiguates the two rules. So we don't want to explicitly disambiguate the two rules. We want to expose the model's inductive bias by measuring how it generalizes to these cases. So then in the evaluation phase, we take examples with the relative clause in the subject and ask the model to form a question based on those declarative sentences. And there are two evaluation metrics that you can think of here. One is exact match. Is the full output exactly consistent with the rule? And another one that's maybe a little bit more lenient but still captures the main question here is whether the first word that the model generates is consistent with the rule. So if accidentally, instead of the word giggle, it's using a different word like jump, then maybe it doesn't really matter to us, right? Maybe we can forgive the model for getting the wrong word there and focus on the fact that it produced the correct word at the beginning of the sentence, because this is what we really care about. Which of the auxiliaries does it want to move to the beginning? So for this project, we took this kind of classic sequence-to-sequence RNN architecture, where you run one recurrent neural network on the input, and then you take the last hidden state of that recurrent network, and that becomes the first hidden state of a new recurrent network that produces the output. And we tried a bunch of variants on this architecture. The details don't matter. So these are three types of recurrent units, and we tried to attention. We actually had two different kinds of attention, so that becomes a 3x3 design. We have three types of recurrent units and three variants of attention, like no attention, location-based attention, and content-based attention. We tried to do our due diligence and look at as many architectures as we could at the time. And here are the results. So most of these architectures, most of these combinations, learn to do the task very well. So they're able to form questions that have a similar structure to the sentences that they encountered in training. Even though those are new sentences, those are not the same sentences that they saw in training, but they have similar syntactic structures to the sentences that they saw in training. So these are very high accuracies. Now, when you look at their generalization behavior, first of all, they do make a lot of exact match errors, as we'll see in a bit. But maybe interestingly, some of these combinations do produce the correct auxiliary as the first word of the sentence. So it's hard to interpret why this particular combination generalized in this way and the other combination generalized in the more linear way. We do make some attempts to understand why different models have different inductive biases here in the paper that I can send you to later. But the potentially promising thing here is that there are some combinations that do have the inductive bias that we think humans do have. But when you take a closer look at the exact match errors, you see that actually in a pretty small proportion of the cases, did the network really produce the exactly correct question, which is here, can the dog who will yawn visit my yak? So usually the errors that they would make, one class of errors is they don't delete the auxiliary from the original position. So the question that they form is something like, can the dog who will yawn can visit my yak? Which is actually a type of error that children also make. But so I guess we felt that we tried a lot of architectures, and it looks like none of them had the bias that we think humans have. And maybe that's not surprising. I mean, it would be somewhat strange if a neural network architecture that didn't have any linguistic structure in it or any bias that we explicitly tried to put into it, just like magically generalized in the way that we think humans generalize. So the next thing we did was to actually explicitly implement the structure sensitivity bias, and for that we used the technology it's not our own technology, it existed before, of tree-based recurrent neural network. So the idea here is that instead of the standard recurrent neural network that processes the sentence from left to right, which gives it a pretty clear linear bias or linear representation of the sentence, we force the network to process the input based on the structure of the sentence. So we know that the word your and zebra together form a constituent. So and also the same with does giggle. So what we're going to do is first we will create a representation, a vector representation of each of the phrases, and then we will combine those vector representations to a larger vector representation of the sentence. Instead of left to right, we follow the structure of the sentence. And we do the same on the decoder side, and that actually works, right? So here, you're being very explicit about the generalization behavior that you want the model to do. So that's maybe not so surprising that it works, but because we're basically holding the model's hand, but it is a proof of concept that we were able to get the correct generalization behavior. Here's the accuracy. The relevant line here is the last line. So we get very high accuracy, and even when the model does make errors, they're the kind of errors that children also make. So I guess I should end here. What I want to, just like in a couple of words, what I wanted to take away Yeah, so we have very strong learners that are able to approximate the training data very well, but they actually do it a little bit too well. So we can think of it as overfitting to the training set, and not in the sense that we memorize specific examples from the training set. We do also do that, but that's fine. But that we capture all of the different statistical patterns that exist in the data set, even ones that we know are not relevant to linguistic tasks. We as humans know that, but the model doesn't know that. It doesn't have any bias that tells it to ignore those kind of random aspects of the data set that arise from the way that it was generated, but are not kind of plausible linguistic features that should guide the model's behavior. There's another set of generalization issues that I didn't touch on today, but I think are very related, which is sample efficiency. So when you have a very weak inductive bias, we also need a very large number of examples to get the correct behavior. and that's, I think, part of our discussion before, you need to see a lot of counterexamples for every possible potential heuristic to abandon that heuristic and learn the correct thing. So this is just a plot of how the training data sets have kind of dramatically increased in size in the last few years. Nowadays, we have even larger training data sets, but these are the people train neural networks on hundreds of billions of words. It's just an enormous number of words that is much, much bigger than the number of words that humans need to learn language. So you can't even see the bars here because the scale is so out of whack, but if you look at it on a log scale, so the English learners can learn basically everything they need to learn about English from maybe 50 million words, whereas our neural networks need many thousands of times more words than that. So I think that if we had the right inductive biases in our neural networks, we just wouldn't need that vast amount of data. And that is what I think we should spend more of our time focusing on getting those biases into the networks rather than scaling our networks up. And that's what I wanted to say today. Yeah. Thank you. Yes, we have maybe time for a couple questions. Yeah.
You know about someone who tried to generalize this between sentences, maybe with co-references or something like that?
I'm actually not sure. Can you give me, to generalize what?
To generalize the graph neural networks over text for larger graphs than more than one sentence.
Right.
Can you repeat the question?
Well, so the question is whether people have tried to take this sort of structured neural network architecture and apply it to cases where there are multiple sentences. Definitely when for those tasks that have two sentences as an input, like the inference task where we have the premise and hypothesis, people have tried that. We have also done that. That's not difficult to do, but I think you're asking about a longer text. I don't know. I mean, maybe. We haven't done that. Okay, yeah.
So, has this kind of research and Blaze work and others, has this led to sort of linguists, more traditional linguists, trying to fight more bias-based methods, or is this work more? And what exactly is the impact of this on the mainstream NLP?
Of NLP or of linguistics?
NLP, has this led? I mean. As an outsider listening to your talk, I would say, well, the thing to do is maybe to abandon the neural networks and go back to real techniques, but I have a suspicion that's not what's actually going on.
Yeah, that's a good question. I don't think it's realistic to abandon neural networks. I think what we need is some kind of hybrid approach, because language, in addition to those structured properties, it also has a lot of facts and quirks and a lot of things that you just need to memorize, and neural networks can do that very well. So I think what we need to figure out is how to tame them and how to get them to have the biases that we want them to have. I mean, in the short term. It's possible that in the long term we should abandon them, but that seems like the... I think that people have... I don't know if it affected the mainstream as in... I think the mainstream for now is maybe still training bigger and bigger models with very simple architectures, like GPT-3. That's an architecture that we've had for a few years. There have been very little modeling innovations there. Just like they train it on a ton of data with many more units. So you can think of that as the mainstream, but I do think that there are at least a few dozen papers that I've seen that try to address the bias issues that we pointed out in the first study that I showed, the inference. And I don't know if the methods have been universally adopted, but I do know that people are adopting them maybe not so much for syntax, but more for fairness. So in the same way that you memorize whatever quirks happen in your training set for syntax, you also do that for things like gender. So if there are certain occupations that tend to skew male in the people who do them, then it's likely that the model will just learn that doctors tend to be male and nurses tend to be female or something like that, and which is something that we don't want the model to do. So we need to mitigate that tendency to be very faithful to the training set in various ways. So I think in that area there's been more impact. I don't know. I feel like we're a little bit out of time, so I don't want to keep people here.
So let's thank the speaker again.